Not relevant. This is just me, the songs. This is not part of the data. This is somewhat random in that when I put the songs in the iPod, I labeled them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It doesn't matter that song 5, which happened 8 times, was NoFX or whatever the hell it was. It could have easily been Pat Benatar just by how I labeled the songs. Totally irrelevant. Here's the relevance. Those are the numbers we saw. How can we possibly measure that for randomness? Let me make sure I did this right. This should sum up to 50, right? Let's make sure. 9, 13, 19, 23, 31, 36, 40, 50. Good. How can we test to see if that's random enough? Notice how I called that the observed. That's what we observed. That's fairly standard statistical language. O for observed. How can we test it for randomness? Yes, well, I love this idea. L1, L2. What will go in L2? What do you think? Any ideas? What frequencies? I love this idea. The observers are going to go in L1. These guys, let me just erase it. These guys are irrelevant because the songs, it doesn't matter which author the song. So L1 for sure. I love that idea. Although we're going to do most of this math on the board today before we start using technology because this is vastly different than we've done to this point. So L1, what's going to go in L2? I love the idea L1, L2. Yes, that's perfect. L1's going to go here. What do you think is going to go in L2?
The number of times it should have happened?
The number of times it should have happened, which would have been what?
5.
Which would have been 5 for every single one. And that's called the expected. Thank you, friends. That's called the expected. You compare what you saw to what you should have seen if the null hypothesis is behaving itself. Which would have been 5 all the way down. Beautifully said, my friends. Which also sums to 50. This is what you saw. This is what you should have seen if the null hypothesis is working properly. Good. Very good, very good, very good. So that would be L1 and L2, although I don't want to go right to L1 and L2 right now. I want to focus on the mathematics first. I gave you guys a program back in 243 called GOF, G-O-F, that will do all this math for us. But it's a black box, and I try to strike down black boxes in this class as much as I can. I want you to understand what the black box is doing. What's the matter, Mel? Tell me what's on your mind.
Oh, I was just black box. It just sounded funny.
Oh, well, I mean, you think about every time you guys run one of those stat tests in your machine, and you press draw, and it draws the curve and spits out a p-value and a test statistic, that's a black box. It's data going in and a result coming out, and the black box hides what's going on. That's why I always start, whenever we start a new idea, by breaking the black box down. Right? A black box is just a misfit. This is a black box. Literally, it's actually colored black. And you type, and an email goes to somebody, or a Facebook post, or a tweet goes to somebody. How does it do that? It's a black box. A little magnet, a little hamster, a little carrot. All right. How are we going to see if this and this are statistically the same? What do you think? Ideas. What can we do with these? Think back to 243, because you did it weeks ago in this exact same setting. We can!
So when we did those random tests, like you go in your calculator, there's like several different random tests.
Absolutely, brother, absolutely, but this is going to be the result of one of those tests, if you will. So we've taken care of that already. So now what I'm saying is, we now have, you're talking about making it dynamic, making it Monte Carlo. Awesome, by the way, awesome. What I just showed you when I was hitting F9 was the exact same thing. So now we've got a data set. I want to statically see if this agrees with this. Any ideas what we can do? Divide it. So do 3 divided by 5 to get 0.6. Yes? 7 divided by 5, 1.4. If I'm doing this correct, I think I'm doing this right. 4 divided by 5, 0.8. What numbers would that then tell us? I love that idea. I love that idea. If it's less than 1, if it's less than 1, then it's under-occurring. If it's greater than 1, it's over-occurring. If it's equal to 1, it's occurring perfectly. I love that idea. The problem is nobody does that. It's a freaking awesome idea. Why would nobody do that? I know why. I think I know why. I think I know why. Multiplication and division deal with error differently than addition and subtraction. They compound the error at a higher rate, which means you're going to introduce more error than we have to. That's my guess as to why nobody does it that way. That's a freaking awesome idea, though. But unfortunately, I just gave you the answer too. Veronica, what do you think? That I think introduces less error. If you simply subtract L1 from L2, or the observed O minus E. Although, Danielle, I wouldn't say throw away that division idea. That's actually pretty clever. It's actually pretty clever. It just creates a different random variable. But I do worry that it would create a little too much error. I could be wrong. I could be completely wrong. So O minus E is what is actually done. See if there's a difference. So 3 minus 5, negative 2. 7 minus 5, 2. Negative 1, 0, 3. Negative 1, positive 1. Negative 1, 2. Negative 3. You know. In an ideal world, which as Melanie correctly surmised over there earlier, will never happen, what should all those numbers be? In a perfect world, they should all be 0 because there would be absolutely no deviation from the average. But that will never happen. Even our large sample set will never be exactly equal to 0. We talked about that back in 243. We'll talk about it again now. What should we do with that column? What do you think? What should we do with that column?
Add them together.
Add them up! Go ahead, add them up. What do you get?
Negative 4.
You get 0. What the hell? The hell? It has to be right, doesn't it? Doesn't it have to be 0? It will always be 0. Explain to me why it will always be 0. And please realize what I'm saying. It'll always be 0 no matter what these numbers are, as long as they sum to 50. Tell me why it has to be 0 regardless. M, go!
50 minus 50 is 0.
Because you're essentially doing all of these minus all of these, which has to be 0, no matter how these are distributed. Even if that was 50, and all of these were 0, 50 minus 5 would be positive 45, and you'd have 9 negative 5s, which would sum to 0. It's a balance point again. It's once more, we had the exact same thing happen, do you remember, in 243, with two of our very favorite characters in 243? Bert and Ernie. We had the exact same thing happen with Bert and Ernie when we got to this very point. We had the data points, and we subtracted the averages, and those differences, just like this, summed to 0. How did we fix it back then? Do you remember what we did to fix it back then? Do you remember? It's okay if you don't. The easy fix to fix this problem, that actually probably doesn't seem easy. We squared it. Remember doing that? You can say no. It's okay. It's been like 8-10 weeks. We squared the differences to get rid of the negatives, which is what's causing the issue. We had a great discussion back then, too, about what would have been more logical to do than squaring. Like, for example, just taking the absolute values would have been logical, too. But there's a mathematical reason, which unfortunately we need calculus to fully understand as to why you don't do that. So just trust me on this one, if you will. I give you more later if you want. 4, 1, 0, 9, 1, 1, 1, 4, 9. Don't worry about summing that. Don't worry about summing that. Nick, go! You're just scratching your head.
No,
You're just scratching your head, you're mad. Now, at this point in 243, we had the squares, and then we dealt with them in the following way. We took them and divided by the sample size. Okay, so we turned it, if you will, into an average. Something similar happens here, and I have a mathematical reason to explain it to you momentarily. We're going to make one more column, and I promise you technology will do all this for you after this. I promise. This is the last time we'll fill a board with mathematics in this class. We take that, square it, and we divide by the expected number. We divide by the expected number, which is over here in this column. So you take each of these and divide by each of these. So Danielle, we're getting, if you will, at the heart of what you were talking about, but we have to divide by the differences first, not just the occurrences. So we're getting at the heart of what you were talking about with the division, but we have to set it up in this way in order to make it fit the distribution we want to use here. So 4 divided by 5, just 0.8. 4 divided by 5, 0.8 again. Notice how 3 and 7 are the same distance away from 5. One's up, one's down. But they're the same distance away, thereby yielding the same variance over here of 0.8. 1 divided by 5, 0.2. 0. 9 divided by 5 is 1.8. Check my math on this one. 1 divided by 5 is 0.2. 0.2. 0.2. 0.8. And 1.8 again. Whew. Yes, you're exhausted from this. I appreciate that. It's kind of exhausting. We did all of this to get that column. That is the column that statisticians have created. And if you add that column up, that's actually your test statistic. If you add that column up, if you sum up, I'm going to go, can we see this on the camera? We can. If you sum up the column that corresponds to this, that's actually your test statistic. So let's do it. 1.8, 3.6, 3.8, 4, 5, 6.8. Did I get that right? 6.8?
That's what I got.
Good, 6.8. Good. That's your test statistic. So if I just told you that was your test statistic, 6.8, what would your gut go to? 6.8 what?
Standard.
Of course you would. And you would go that if that's 6.8 standard deviations, is that significant?
Yeah.
Yes, it is. But it's not 6.8 standard deviations. This is our first non-Z, non-T distribution. This guy right here is called the chi-square test statistic. When you're looking at your little template there, down at number 6, yes, this is, I know, we've learned proportions are always Z, means are always T, until you go with more than 2 of them. That's the one time you have to shift out of those distributions, because these won't fit on the old distributions, because the old distributions allow for no more space than just 2. Do you have to memorize this? No, of course not, because technology will take care of it for us. But you have to know what to use, which test to use. Now, I want you to understand why. Think about this before we go to the graphic. Think about this before we go to the graphic. What is the least possible value this could have? Go back to how we constructed it. What is the absolute least possible value this could have? 0, right? It can't be negative. We took care of that right here. So the absolute least it could be is 0. Well, that breaks the rule of standard deviations, because standard deviations can be negative. But the problem with negative standard deviations in this case is you've got 10 things that you're juggling at the same time. You can't talk about a negative standard deviation, which means something is below something else, because you've got 10 things. It's not just 2 things anymore. That's a problem. So the absolute smallest this can be is 0, as Melanie said, is it's a very extreme case anyway. So this is either 0 or positive. 0 or positive. So the question then becomes is, how far out is 6.8 from 0, and does it arouse suspicion? Let's find out now. That's the point right now. What do we need with that test statistic? What tells us how to make a decision? We need a p-value. We need a p-value that says it's either small, which means the randomizer is not working, or it's big, which means the randomizer is working. So, let's go over to here. Break the string. That's why I don't want all this put together. There we go. Okay. Now, look at this beautiful thing. That is the graph of what's called the chi-square distribution. Folks at home can't see it because I didn't turn the camera. Don't get nervous.